this video, we're going to discuss a vector space. And a vector space is a fairly abstract idea, but we're going to start with a very concrete set of rules. And the rules are going to sound very familiar to you because you've been working with a vector space for a long time. The set of real numbers is a common, very good example of a vector space. The set of complex numbers is also a very good example of a vector space. So you've been working with a vector space without realizing necessarily that you have been working with a vector space. So a vector space is a set of objects, and we're going to call the objects vectors. Do not necessarily think your vectors have to be arrows. They could be, but they could just be any objects. And you're going to define two operations on these objects, one called addition and the other called multiplication by a scalar. And 10 axioms are going to need to hold true. And the axioms are listed below. And like I said, they're going to be very familiar to you because they hold true for the set of real numbers. And you learn these axioms in algebra class for the set of real numbers because the set of real numbers is an example of a vector space. And the axioms must hold true for all vectors in your set, in your vector space, and for all possible scalars. So the 10 axioms are listed here, and they're not necessarily in any particular order. The book has listed them in this order. One of them, though, is an important idea that it's given kind of a special name. It's called closed under addition. And it means that if you do the operation that you're going to call adding on the objects, the sum or the result of adding has to also be in your set. So if you add two items, the result of adding has to remain in the set. So the set is closed under addition. Add any two items, you get something that is still in your vector space. And another important of the axioms also is given a name, and it's called closed under scalar multiplication. So similar to the idea of closed under addition, if you multiply by a scalar, that result has to stay in the set. So take any vector in your vector space, take any scalar that you have defined, and if you multiply according to however you're defining multiplication, that item has to stay in your vector space. So that's called closed under scalar multiplication. Then the order that you add is not going to matter. That's axiom number 2. U plus V equals V plus U. The association that you add does not matter. So if you add U and V and get that result, and then you add W, it'll be the same as if you added V and W and then added U. So again, that's the associative property of addition holds true. Axiom 4, there has to be something that's considered a zero, and the definition of a zero means that when you add the zero, it does not change the value. That's going to be your definition of what a zero means. There also needs to be an opposite for every vector, and what it means to be an opposite is when you add two objects that are opposites, you need to get 0. So every item or every object in your vector space needs to have an opposite in the vector space also, because you need to be able to take any item and add its opposite to get 0. And we already talked about being closed under scalar multiplication. If you multiply by a scalar, you should be able to distribute over addition. If you add two scalars together, it should be the same as if you distributed the object over the addition of those two scalars. So that's the C plus D times vector U should equal C times U plus D times U. And you should be able to associate scalars. So you should be able to multiply by D and then multiply by C, or multiply C and D together and then multiply and any object u by that and get the same result. And there needs to be something that's considered a multiplicative 1. So something that's considered 1, so that the scalar 1 times one of your objects doesn't change the value of the object or doesn't change the object. Again, the set of real numbers is an example of a vector space. The set of complex numbers is an example of a vector space. And so these rules very naturally will apply to real numbers and complex numbers. But vector spaces in general can be more abstract ideas. I have had assignments where students were supposed to come up with an example vector space, and students have created whole universes of characters for video games, and there's been a special neutral character that they call the zero, and if that character combines with other characters, the other characters' powers stay the same. There are characters that cancel each other out, and so they kind of both work to destroy each other, thus creating what they consider the zero. Anyway, they make up characters in this video game. Then the characters are the objects of their vector space, and they make up a definition of adding. Sometimes it's adding powers together. They make up a definition of scalar multiplication. Sometimes it means your power ramps up or gets decreased by some multiple. So you might double your power, or your power might get reduced to a third. I'm mentioning that because I do want you to realize that despite the fact that this set of rules very naturally just seems like, okay, these are the rules of algebra, that's because you've been working with an example vector space in the set of real numbers and the set of complex numbers. But you can define addition to be something different than counting on your fingers and putting two numbers together like we're used to addition. It can be some sort of operation like in a video game. So we're going to talk through a couple of examples, and here our set of objects are expressions of the form some scalar times cosine squared of some variable theta plus another scalar times sine squared of the same variable that was plugged into the cosine squared. So our objects have to fit that expression form. Is it closed under addition? Well, take two objects of that form, so some scalar times cosine squared plus another scalar times sine squared, and make up another version, so a different scalar times cosine squared plus a different scalar times sine squared. If you add them, you're going to get some scalar. If you add a1 and a2 together, you'll just get a different scalar times cosine squared plus a scalar times sine squared. So yes, I get the same form. So it's closed under addition. Does the order that I add matter? No. If you plug numbers in and you look at adding, if you mix up the scalars in different orders, or you add sine squared and cosine squared in different orders, you're still going to get an equivalent expression. So it is closed under addition, and it also satisfies the commutative property where the order that you add doesn't matter. If you take objects of the form that we've been talking about and you associate two together and then you add a third, you'll get the same overall result as if you added the second two and then added the first one. So the associative property of addition holds true for expressions of this form, a scalar times cosine squared plus a scalar times sine squared. And we can create a zero vector by having both of the scalars be zero. So if A is 0 and B is 0, then you're going to get the expression equal to 0. And then when you add that 0 to any other vector in our set, you're going to get the same vector value. You're not going to change the value of the vector. So you could create a 0 in the set by having your two scalars be 0, and also when you add 0 to an expression of this form, it doesn't change the value. So that, again, that's important to have something serve as the 0. Is there an opposite? Yes, there is. Just make your scalars the opposite of the scalars of some other expression of the form. And you can see that you easily can do that because every real number has an opposite. And when you add, you get 0. Again, 0 technically is a scalar that doesn't have an opposite, but it's the 0, and the 0 is special. Is it closed under scalar multiplication? Yes, it is. If I have an expression that's a cosine squared plus b sine squared, and I multiply by another scalar, I'm just going to create a different scalar times cosine squared plus a different scalar times sine squared. It'll still be of that same form. I can associate the scalar multiplication, so some constant scalar times another times the form, a cosine squared plus b sine squared is going to give me the same thing as if I multiply the c and d together and then apply it to the object that I had. So rule number 9 holds true, and I can also distribute scalars over vector addition. So if I added two of my forms together and then multiplied by some outside scalar, I get the same thing as if I individually multiplied the vectors by that scalar and then added. So rule number 7 holds true also. Then if I added two scalars together and multiplied by a vector, it will be the same result as if I individually multiplied the vector by those scalars and then added. So rule number 8 does hold true for the objects of my form, a scalar times cosine squared plus some scalar times sine squared. And then there is also the existence of a multiplicative 1, a scalar 1, so that 1 times one of my forms equals the same form that it was. So multiplying by this scalar 1 does not change the value. So it passes all of the properties, and it thus is a vector space. After that last example, you might think, well, everything's going to be a vector space. It's not possible to not be a vector space, but you can certainly think of sets that are not going to fit the definition of a vector space. Consider the set of all 3x3 matrices in which the corners are integer multiples of 3. So my corners have to be some integer multiple of 3, like 0 or 3 or 6 or 9 or 12, etc. Now, 0 exists because every element in the matrix could be 0, because 0 is a multiple of 3. And it is closed under addition because if you added two matrices that were of that form, the corners would be 3 times an integer plus 3 times some other integer. You could factor the 3 out, and it would still be 3 times some integer. So it does have a 0. It is closed under addition, but it is not closed under scalar multiplication. Because if we assume that we're making this set out of real numbers, so your scalars could be any real number, when you multiply by a scalar that's not a multiple of 3, then your corners are no longer going to be an integer multiple of 3. So for example, if I multiply by a half and my corners were 3, so if my corner was 3, 3, 3, 3, and I multiplied by a half, now my corners are 1.5, and 1.5 is not an integer multiple of 3. So it is not closed under scalar multiplication with the assumption that scalars could be any real number. So this does not form a vector space. Now, if instead we defined our set, our vector space, to be all 3x3 matrices. So not just 3x3 matrices that have integer multiples of 3 in the corner, but any 3x3 matrices. It has a 0 because you could make every element 0. And when you add that matrix of all zeros to any other 3x3 matrix, it's not going to change the value. It's closed under addition because if I add two 3x3 matrices, I get a 3x3 matrix. It's also closed under scalar multiplication. If I took a 3x3 matrix and I multiplied by any scalar, every item gets multiplied by that scalar, but it's still a 3x3 matrix. So it has a 0, it's closed under addition, and it's closed under scalar multiplication. You can check that all of the other remaining axioms do hold true. For example, there is an opposite. Just make all the entries the opposite, and when you add two matrices that are filled with opposite entries, you get the 0 matrix. There is a scalar 1 that you can multiply by, and it doesn't change any of the entries of your matrix. All the different distributive properties hold, and all the different associative properties also hold true. So the set of all 3x3 matrices does form a vector space. This next example is about a set of objects that you may or may not be familiar with. We're going to say that our set consists of all objects of the form A mod 5. A mod 5 is the remainder when A is divided by 5. Now, for this vector space, we are going to define scalars as only integers. Okay, we're going to make up that's our definition of a scalar. And if we follow that definition of a scalar and we define addition and multiplication as shown below, it does satisfy all 10 of the axioms. So how we're going to define addition is that A plus B mod C would be, for example, 14 plus 17 mod 5. In our set, we're doing A mod 5. You would add 14 and 17 together and you would get 31 mod 5. 31 mod 5 is 1 because when I divide 31 by 5, I get a remainder of 1. So how you're going to define addition in this vector space is you add the two items and then you do the mod 5. How we're going to define scalar multiplication is we're going to multiply two scalars together and then we're going to do the mod 5. So I have an example here where I'm showing how to do the multiplication with mod 6. So 4 times 7, so we're multiplying 4 times 7, and you get 28. 28 mod 6 is 4, because you get a remainder of 4 when you divide 28 by 6. So that's how we're going to define our multiplication. So with that definition of addition and that definition of multiplication, and assuming that scalars are only integers, all of the 10 axioms are satisfied. It is closed under addition, and it's closed under scalar multiplication. You can define a 0. For example, 5 mod 5 is 0 because you have a remainder of 0. If you take 5 mod 5 and you add 7 mod 5, you get 12 mod 5, which would be 2, and 7 mod 5 is 2, and 2 added to 0 is still 2. So you can see that I can define a 0. I'm going to make it 5 mod 5. 5 mod 5 is 0 because the remainder is 0. And when I add 5 mod 5 to any other item, I get the same thing. It doesn't change the value. So my definition for 0 works. I also can define opposites. So for example, you could find something that you would add and get 0. For example, 523 mod 5 is 3. add 523 mod 5 to 2 mod 5, and you get 525 mod 5, which has remainder 0. And all of your distributive properties end up working, all of your associative properties end up working, the order that you add doesn't matter. So if you carefully study the arithmetic, how we've defined addition, how we've defined multiplication here, and you just in your mind you picture the world only existing of integers, then it does satisfy the definition of a vector space. So with our more abstract thinking in that past example and picturing the world only existing of integers, that mod arithmetic did form a vector space. Now notice we had to define the vector space with mod 5. If you wanted to use mod 6, you would have to separately, have a whole set with just mod 6. Also, if you allowed scalars to be any real numbers, then it's not going to fit the definition of a vector space. So again, you had to think a little bit more abstractly, and you had to imagine scalars only being integers. But with those definitions, it did form a vector space. Now, a subspace of a vector space is a subset. So imagine a vector space, and then you're taking a part of that space. It's defined to be a subspace if your subset contained the 0, and if your subset is closed under addition and closed under scalar multiplication. Meaning if you just take part of your original vector space, but as long as the part you took stays closed under addition and closed under scalar multiplication, then it's a subspace. So when you add two things, it has to also be in the subset. When you multiply by a scalar, the result of that has to stay in the subset, and 0 needs to be in the subset. If you took all the points in a plane and the plane went through the origin, then that would form a subspace of R3, of the third dimension. Why? Well, the origin is in the plane because we said it goes through the origin. If you take any 2 points on the plane and you add them, you also end up with another point on the same plane. If you take a scalar multiple of any point on the plane, that resulting new point will also be on the plane. So again, a plane through the origin is a subspace of R3. The same is going to hold true if you're working in R5 or R4, some other dimension. Your plane would, just be a dimension lower than what dimension you're working with, but you need the origin to be in your subspace. Otherwise, it's not going to fit the definition of a subspace. If you had a plane that did not contain the origin, that set of points does not form a subspace of R3. It's a subset. I mean, any plane in R3 is a subset of R3, but if your plane does not go through the origin, it does not form the definition of a subspace. 0 is not on the plane, so obviously it breaks that rule. But also, if you took any 2 points on the plane and you added them, you don't get a point that is on the plane. I mean, you do if your plane contains the origin, because the initial point of any vector on the plane would be the origin. But if your plane does not go through the origin, then when you add points, you don't necessarily get a point that stays on the plane. For example, we could take the plane 5x minus 2y plus z equals 4, and a couple of points that are on that plane are 2, 2, negative 2, and 1, 1, 1. When I add those points together, I get 3, 3, negative 1. But if I take 3, 3, negative 1 and I put it into my equation of the plane, 5 times 3 minus 2 times 3 plus -1, I don't get 4. So that point, that new point, 3, 3, -1, is not on the plane. And if I take a scalar multiple of one of those points, so if I take 8, 8, -8, which is 4 times the 2, 2, -2, I also get a point that doesn't satisfy the equation, and so it can't be on the plane. So this subset fails all 3 of the criteria to be a subspace, and so it's definitely not a subspace. But even if it had failed one of them, it would still not be a subspace. All 3 of those criteria have to be true. It has to contain the zero, it has to be closed itself under addition, and it has to be closed itself under scalar multiplication. In this example, we're going to imagine vectors in the 4th dimension of the form 2 times some scalar plus 4 times a scalar for the first item, and then the second item in the vector is going to be 2s, and then the third item is going to be 2s minus 3t, and then the fourth one is going to be 5t. The s's have to be the same and the t's have to be the same. Otherwise, I would have used different letters. So if I pick s to be 1 and I pick t to be 5, then the first item of one of the vectors is going to be 2 plus 20, or 22. But then the second item in the vector has to be 2, because I said s is 1. And the third item in the vector has to be 2 minus 15, or -13, because I said t had to be 5. And then 5t would be 25. So just by the way, when you're making something up or you're reading something and the exact same variables are used, it means that, within the same conversation. So I'm listing the vector here and I'm listing 2s plus 4t and then 2s. The s's are assumed to be the same. 0 is in it because s and t could both be 0. And if I add elements of that form, I could factor the 2 and the 4 out, and I get something of the same form. You add s and r together, and it's going to be the same as the s and r in entry number 2 of the vector. If I multiply by a scalar, then I get something of the same form. So all 3 of the criteria are met, and thus it forms a subspace of R4. And if you made a slight adjustment and you said that the second entry was just 2 and not 2s or 2t or 2 times some variable, that set of vectors in R4 does not form a subspace of R4. Again, R4 is a vector space. We have 2 different examples here of subspaces. One is a subspace, the second one is not. And the reason why the second example on this slide is not a subspace is because the second entry is just stuck at 2, and you can't make it equal to 0, so 0 would not be in that subset. What about if we made the set of all polynomials of the form p of t equals b plus ct squared, where b and c are real numbers? Is that a subspace of the vector space of all quadratic polynomials? So by the way, if you took all quadratic polynomials, so a t squared plus bt plus c, that does form a vector space. It has a 0 because you could make all the coefficients 0. It has an opposite. If the order that you add doesn't matter. It follows all the distributive properties, etc. Okay, so we're taking a subset b plus ct squared. Now it has the 0 because b and c could both be 0. And if I add 2 forms of the form we're talking about, I get a constant plus a scalar times t squared. It fits the same form, so it's closed under addition. And if I multiply one of those forms by a scalar, I also get a number plus a coefficient times t squared, so it fits the form. So it satisfies all three criteria to be a subspace. So it is a subspace. A couple of other examples of vector spaces related to our study of linear algebra is for any matrix, like the matrices that we've been using in linear transformations or we've been using to solve systems of equations, the null space and the column space are both examples of vector spaces. They both contain 0 because the null space contains 0 because 0, 0, 0, 0, or however many zeros you need, depending on what dimension you're working in, is always a solution to ax equals 0. Again, that's the definition of the null space, is your matrix A times some vector equals 0. The null space is the solution set to that homogeneous equation, a times x equals 0. The column space is the set of all possible linear combinations of the vectors that make up the columns of matrix A. So 0 is in that because you could make all of your scalars that build your linear combination 0. So you could take 0 times column vector 1 plus 0 times column vector 2 plus 0 times column vector 3, and you'll get 0. So 0 is in both of them. And if you add any two vectors that are in the column space, they're obviously still in the column space because they're also a linear combination of the vectors. And if you take any two solutions that make ax equals 0 and you add those two solutions, you're going to get another vector that is a solution for ax equals 0. And if I multiply by a scalar, so if I take any vector that's in the column space and I multiply by a scalar, well, it still is a linear combination of the vectors. Thus, it's in the column space. And if I have a solution to ax equals 0 and I multiply by a scalar, that vector will also still be a solution to ax equals 0. And all of the other axioms hold true. You could kind of trace through them with the algebra. It's kind of interesting, though, to kind of compare and contrast the null space and the column space. So again, the null space is the solution set when you set ax equals 0. The column space is the set of all possible linear combinations of the vectors that make up the columns of A. So the null space is a subspace of Rn, whereas the column space is a subspace of Rm. The null space is implicitly defined. You're given the condition ax equals 0, and you're trying to find all vectors that satisfy that equation. But the column space is explicitly defined as the set of all linear combinations of vectors that you're given. And if you're trying to find your null space, you have to take your system and RREF it. I know we have calculators that do that for us fairly quickly, but the column space, your columns are right there in your matrix, and then you know that you're just taking those and making linear combinations of them, so it's kind of more explicitly defined for you. If you just are given the matrix A, you can't automatically see what's in the null space. Again, you have to do some work, like RREF it. Whereas, given the columns, you can kind of automatically see some of the vectors because the columns themselves are in the column space. And you know that any vector in the null space makes A times it equal to 0. That's by the definition. For the column space, if it's in the column space, then you know that A times it is consistent. Like if you set up that equation, A times x equals V that's in the column space, you know that there's a solution. Otherwise, it wouldn't be in the column space. It would not be a linear combination if that equation did not have a solution. And given a specific vector, it's easy to tell that it's in the null space. If you're given a specific vector, just take A times it. If you get all zeros, then it's in the null space. If you don't, it's not. But if you're trying to test whether a vector is in the column space, once again, you end up having to set up a system of equations and RREF to get your answer. And the null space is only 0 if and only if the equation AX equals 0 has a trivial solution. And the column space spans all of Rm if and only if AX equals B has a solution for every B in Rm. And the null space equals 0 if and only if the linear transformation is 1 to 1. The column space is all of Rm if and only if the linear transformation is onto. So just some things to be aware of related to the null space and the column space. First of all, it's good for you to recognize that the null space literally is a vector space, and the column space of any matrix A is also a vector space. And just a reminder, the word kernel is another name for the null space, and we usually use it when we're specifically talking about linear transformations. So it's the set of all vectors that you transform into 0.